Good morning, students. It is for 11th Physics, chapter number 5, lecture number 5. In this lecture, we will discuss about the maximum speed with which a vehicle can turn in circular track. We will take two cases. One is when the track is simple and second when track is banked. So first we are taking simple circular track. This is simple circular track. This is the vehicle, and suppose this vehicle is traveling in the circular track with velocity v. So v is the velocity of the of this vehicle. Now, because it is moving in a circular track, so it will experience outward force, a centrifugal force. So wheels which are in contact with this road, it will tend to move in outer direction, so these wheels will experience force in this direction, force of friction. Due to centrifugal force, these wheels will experience force in outward direction. It will tend to leave the circular track. So force of friction will come into play, and direction of force of friction is always opposite to impending motion or motion. Impending motion, motion which is pending. So force of friction will be in this direction. So you can say force of friction will be toward the center of the circle. So now there will be two forces. One will be force of friction toward the center of the circle, and second will be centrifugal force which will be just opposite to this force. If this inward force, that is force of friction, will be equal to or greater than the outward force, then vehicle will remain in track. This force of friction is self-adjusting. It will adjust up to that certain limit. So the center, force toward the center, you can say centripetal force, should be equal to or greater than the outward force. What will be outward force? Outward force will be mv square by r. We know centripetal acceleration is v square by r multiplied by mass, that will be the force. So that will be the outward force. And force due to friction is, we know, mu mg. So suppose mu is the coefficient of friction. So mu mg is force of friction. If this force of friction will be equal to or greater than outward force, then vehicle will remain in tracks. It means this inward force should be equal to or greater than the outward. Now simplify this equation for v. This m will be cancelled. So what will be v? Mu r z its under root. So if a vehicle will travel in this track with a velocity equal to or less than under root mu r z, then it will remain in this track. Suppose this surface is frictionless. Suppose mu is 0, then velocity will be 0. So you can say this vehicle will not be able to move in this circular track, it will leave the track. So to avoid this problem, banking of tracks is done. So first of all, what is banking? In banking, one end, suppose this is circular track, this road was in level. Now in banking, one end is raised, it is raised like this. Center in this side, center is in this side, it is raised like this. And this angle with this raised end and this horizontal, that is called angle of banking. So this is the angle of banking. In this case, angle, suppose my hand is showing horizontal and the span is showing the raised. So the angle between the span and this hand is called angle of banking. This is horizontal. Now this end is raised. It is horizontal, now it is raised like this. So it is raised like this. This angle is angle of banking. Now vehicle is traveling, there is a vehicle on this. These are wheels, R is the radius. Weight of this vehicle, weight always acts vertically downward, so weight of this vehicle will act vertically downward. It will act, this mg, m is the mass of the vehicle, mg will act vertically downward. Normal reaction always acts perpendicular to object, so draw perpendicular on this object. That will be normal reaction. I am representing it by R. Extend this line and extend this line as well. This angle is theta, so this angle will also be theta. Its vertical opposite, that will also be theta. So that angle will also be theta. Now we will resolve component. Component of this R along this direction will be R cos theta. Perpendicular to first, perpendicular to this line, so that will be parallel to horizontal. This line is parallel to horizontal. It is R cos theta, so it will be R sin theta. Now it is moving with velocity v. It will experience force in outward direction. So due to that, force of friction will come into play, which will be along this direction. Force of friction is always tangent to the surfaces in contact. So that will be direction of force of friction. Now we can resolve this force of friction. This angle was theta, so this angle will also be theta. These are two parallel lines and this third line is cutting them. So that angle will also be theta. So component of F along this direction will be F cos theta. Perpendicular to first, that is along mg, that will be F sin theta. So these are the different forces. These are the different forces. Now R cos theta is upward force and mg and F sin theta are just opposite. So it means these two forces will be equal because there is no moment along this direction. It means R cos theta will be equal to mg plus F sin theta. Or we can say R cos theta minus F sin theta will be equal to mg. It is our first equation. Now force toward the center is R sin theta and F cos theta. These two forces are acting toward the center. And outward force will be centrifugal force, which is mv square by R. So if inward force will be equal to or greater than the outward, then this vehicle will remain in the track. So condition for the vehicle to remain in track is inward force, which is R sin theta plus F cos theta. It should be equal to or greater than the outward. So it should be equal to or greater than the outward, which is mv square by R. V square by R is the centripetal acceleration or acceleration of a particle moving in circular track, and m is the mass. It is our second equation. Now if I divide second equation by first, so I am dividing second equation by first. So R sin theta plus F. I am substituting value of F as well. F is equal to mu into normal reaction. So F is equal to mu into R. So I am substituting that value. Mu R cos theta equal to greater than mv square by R. Now I am dividing this second equation by first, so divided by first is r cos theta minus f is equal to mu r, so it will be mu r sin theta, it is equal to mz, so it will be divided by mz. This m will be cancelled. R is common in numerator as well as in denominator, so that will also be cancelled. So sin theta plus mu cos theta upon cos theta minus mu sin theta should be equal to or greater than v square upon rz. Now we will divide this equation by cos theta in numerator as well as in denominator. So sin by cos, that will be tangent theta, plus cos by cos, that is mu, upon cos by cos 1 minus sin by cos tangent, so that will be mu tangent theta v square by r should be equal to or greater than. Now we will simplify this equation for v, velocity. V will be equal to rz. I am writing this mu first, so mu plus tangent theta upon 1 minus mu tangent theta raised to power 1 by 2. Because it was a square, so it will be raised to power 1 by 2. So that will be the velocity. So if there is a banked track, then vehicle will move with this velocity. That will be the maximum velocity with which it can move in that circular track safely. Now what is the benefit? We have seen in previous case when there was no banking, if mu was 0, velocity was 0. But in this case, if mu is 0, if mu is 0, so velocity will be, mu is 0, so this term will be 0, it will be only tangent theta, rz tangent theta upon mu is 0, so this term will become 0, only 1 will be left, so rz tangent theta its own root. So if there will be no force of friction or coefficient of friction between road and tires will be 0, even in that case this vehicle can turn with this or can move with this speed, which was not possible if there was a simple turn. Actually what happens? This is r cos theta, r sin theta. R sin theta is toward the center. So this r sin theta provides some force toward the center. Due to that there is some centripetal force. So required centripetal force, some part of the required centripetal force is provided by this normal reaction. If it is a bank, if it will not be banked in that case, because this angle will become 90 degrees, so its component will be 0. So this is the benefit of banking of tracks. Now next, in previous lectures you have calculated change in momentum. You calculated change in momentum by resolving the momentum in components. I will tell you one more method. Suppose it is any surface, object is moving in this direction with initial velocity, initial momentum pi, and strike the surface, and after that it moves in this direction with final momentum PF, and angle between them is theta. Magnitude of PI and PF may be same. So angle between them is theta. We know what is the change in momentum, delta P. Delta P is final momentum minus initial momentum, that is PF minus PI. This is PF, this is PI. What will be minus PI? For minus PI, just reverse the direction of this vector. So if I reverse this direction, now I have reversed this direction, that will be minus PI. Now there are two vectors, PF and minus PI, they are making an angle theta. So if you know two vectors, we know angle between them, in that case you can directly calculate what will be resultant. Square of first plus square of second plus twice AB into first into second, it's under root. So in this case, what will be delta P? Delta P will be under root of square of first, PF square, I am taking writing magnitude, plus PI square plus twice and root of mod of PF and mod of PI. So that will be into cos theta. A square plus B square plus twice AB cos theta, where theta is angle between these two vectors, or you can say initial and final momentum. In this case, do not take a negative sign in a magnitude, because already we have taken this negative sign. Due to this negative sign, direction of this vector was reversed. So you can say two vectors PF and minus PY were acting at this point. Due to an angle between them was theta, due to that change will be this much, or you can say resultant will be that much. If these two vectors will be equal in magnitude, in that case resultant will be bisector, and if it will not be equal, in that case you can find out what will be angle. So that was all about the change in momentum. Next case. Suppose there are few masses. There are, suppose I say, three masses. They are connected with a string, and suppose these masses are 20 kg, 10 kg, 5 kg, and a force is applied in this direction. Suppose I say 70 Newton force is applied. These are three masses, 20, 10 and 5 kg. They are attached with the help of string, and a 70 Newton force is applied in this direction. We are assuming that these are placed on a surface which is perfectly frictionless. We want to find out what will be tension here T1 and what will be tension in this string T2. We want to find out what will be tension here and what will be tension here. What will be magnitude of T1 and what will be magnitude of T2. In this case, total mass is 20 plus 10 plus 5, that is 35 kg. Total force is 70 Newton. So what will be acceleration? Acceleration will be force by mass, that is 70 by 35, 2 meter per second square. So that will be acceleration in these masses. First mass is 5 kg. Acceleration is 2 meter per second square. So for first mass, 5 into 2, 10 Newton force will be required. Suppose F1 force is required for first, F2 is required for second. So first I will calculate only F1. F1 will be 5 is mass, 2 is the acceleration, so 5 into 2, 10 Newton. 10 Newton force will be required for the first. 70 was applied. So 70 minus 10, 60 will be left, which will be transmitted to remaining two masses. So T1 will be total force minus force required for the acceleration of the first, that is 60 newtons. So T1 will be 60 newtons. Now this 10 kg mass, it is also moving with 2 meter per second square acceleration because all are connected, so acceleration will be same for all. So how much force will be required for this? 10 is the mass, 2 is the acceleration, so 10 into 2, 20. 20 Newton force will be required. 60 was transmitted here, out of that 60, 20 will be required for its motion, so 60 minus 20 remaining will be transmitted here. So what will be T2? T2 will be 60 minus 20, that is 40 Newton. So T1 will be 60 Newton and tension T2 will be 40 Newton. One more procedure. For first 10 Newton force is required, for second 20 Newton force is required. So these two, 20 plus 10, 30 Newton is required. Total was 70, 70 minus 30, 40 Newton. Third procedure. It is 20 kg. It is moving with an acceleration of 10 meter per second square. So how much force is required? 20 into 2, 40. So what should be T2? It should be 40. So you can adopt any procedure. In this way you can find out what will be tension in the strings. If we change the direction of the force, then these tensions will change. Now I am changing the direction of the force. Now I am changing the direction of the force. Force is in this direction. Same force, 70 Newton. Masses are same, so acceleration will also be same, only direction will be reversed, magnitude of acceleration that will be same. So A will be 2 meter per second square. For this 20 kg mass, how much force is required? Mass into acceleration, 20 into 2, that is 40. 40 Newton force is required for the motion of the first. Applied was 70, so 70 minus 40, it will be 30. Now direction of tension, that will also be reversed. Now this tension will be 40 newtons. 40 minus 30 newtons. 70 was applied, 40 is required for first, so 70 minus 40, that is 30 newtons. Now this is 10 kg, acceleration is 2 meter per second square, so how much force is required for this? 10 into 2, 20 Newton. So out of this 30, 20 Newton is required by this mass, so 30 minus 20, 10 will be left. Now the T1 tension will be 10 newtons. So if we change the direction of force, then magnitude of tension will also change. Now I will take a case of rope. Suppose this is rope, its length is capital L, and a force F is applied at one end. At any point, suppose I take this point, at a distance L from that end, we want to find out what will be tension at this point. At a distance L from the end at which force F was applied. So in this case, what is the procedure? We will find out what is the force per unit length. F force was applied, total length was L. So F by L, that is force per unit length. So for this L length, how much force will be required? Force required for L length, that will be F upon L into small l. Remaining will be transmitted in the remaining part. So what will be tension at this point? Suppose I say this point is A. So tension at A will be total force F minus force required for first part or this part, which is F upon L into small l. F will be common. 1 minus small l upon capital L. Or you can say F into capital L minus small l upon capital L. That was the one procedure. There is one more procedure. We know force per unit length is F by L. So for this length, how much force will be required? That will be transmitted through point A, so that will be tension at point A. So what will be tension at A? Tension at A. It will be equal to force required for this length. F by L is the force per unit length, and what is that remaining length? That length is capital L minus small l. It is same result. So you can adopt any method. I will take one more case. Suppose there is a rigid support, and with the help of some string or some wire, a mass m is attached. So its weight mg will act in vertically downward direction. Now at this point, some force F is applied in this direction. So what will happen? It will be displaced like this. At this point, some force of F was applied in this direction, so due to that, it will be displaced in this direction. Suppose that is the position. It is in equilibrium position. Equilibrium position means net force is 0. Extend this line. Extend this line as well. Suppose this angle is theta, so this angle will also be theta. There is some tension T in this string. So component of this T along this direction will be T cos theta. Along the given direction it will be cos theta of that vector. Perpendicular to first, that is just opposite to F, that will be T sin theta. Because this mass is in equilibrium, so downward force will be equal to upward. These two forces should cancel each other, that is directions are opposite, so magnitude should be same. Similarly, these two forces, their directions are opposite, so their magnitude should be same. So T cos theta will be equal to mg and F will be equal to T sin theta. So if you know the force, if you know the sin theta, if you know the value of theta, then you can find out what will be T. And if you know the tension, then you can find out what will be theta. That is, if any physical quantity is missing, then you can calculate that physical quantity using this procedure. That was all about this chapter. With this chapter is over. Now you can solve all the numericals of NCERT. Thank you.